Okay, we continue with the questions based on the power system stability. Continue with the questions based on the power system stability. This is asked in one of the GATE question papers. A 100 MVA, 11 kV, 3 phase, 50 hertz, 8-pole synchronous generator, has an inertia constant H equal to 4 megajoules per MVA. The stored energy in the rotor of the synchronous generator at the synchronous speed is. How you find what is the kinetic energy stored? S into H. S how much? 100 MVA. H how much? 4 megajoules per MVA. And simplifying, how much you get? 400 megajoules. And simplifying, you get the answer 400 megajoules. Now we solve this next question. This is also from one of the GATE question papers. A round rotor generator with internal voltage E1 2 per unit, X 1.1 per unit is connected to a round rotor synchronous motor with internal voltage E2 equal to 1.3 per unit, X 1.2 per unit. So the reactance of the line connecting generator to motor is 0.5 per unit. When the generator supplies 0.5 per unit power the rotor angle difference between the machines is. So this is what you have to calculate here. So represent the alternators as given in the question. So the reactances are given here 1.1, line 0.5, second one is 1.2. E1 2 per unit, E2 is 1.3 per unit. So what is PE now? You write it as E1 E2 by X equivalent sine delta 1 minus delta 2. Because this one you write E1 at angle delta 1. This you write E2 at angle delta 2. Generally we write delta, here 0. So delta minus 0 is delta, we write sine delta. But here we have delta 1 minus delta 2. So calculate this one. PE is 0.5 to 1.3, 1.1, 0.5, 1.2. These are the values given. You have to calculate and find what is delta 1 minus delta 2. How much you get the answer? 32.58 degrees. So you get the answer as 32.58 degrees. Now we solve this next question. This from a GATE question paper. A generator with constant 1 per unit terminal voltage supplies power through a step-up transformer of 0.12 per unit and a double circuit line to an infinite bus bar. The infinite bus voltage is 1 per unit. Steady state stability power limit is 6.25 per unit. If one of the double circuit is tripped, the resulting steady state stability power limit in per unit is. So in the question you are also given this figure, transformer. We have the buses 1, 2 and 3. So how much steady state stability limit with 2 buses, with 2 lines? You write it as EV by X equivalent. E how much? 1. What about V? V also 1. What is the total reactance? Say the reactance of the line is X per unit. What about the reactance of transformer? Given as 0.12 per unit. So it is 0.12 and X in parallel. From this you can calculate what is X. You get 0.08 per unit. But further it is given one of the lines are tripped. One of the lines tripped means we have only one line now. Now what will be the steady state stability power limit? It is EV by X equivalent. Both are 1. Now it is 0.12 plus X. So how much X value is? 0.08. How much you get the answer? 5 per unit. So you get the answer as how much? 5 per unit here. So this is how you simplify and get the answer regarding what is the steady state stability limit with only one of the lines, that is second line tripped. With both lines 6.25 per unit, but with only one line power transmission is decreased. How much? Only 5 per unit here. Now we solve this next question. So power angle characteristic of a machine infinite bus system is PE equal to 2 sine delta per unit. It is operating at delta equal to 30 degrees. So we have to find out what is the synchronizing power coefficient at the operating point. So how to find out synchronizing power coefficients? dP by d delta. 2 sine will become cos. But at which angle? Cos 30 degrees. So you simplify, you get it as root 3 per unit. So on simplifying, you get the answer as root 3 per unit. Now we solve this next question. A synchronous generator is connected to a 11 kV infinite bus through a transmission line. The reactances of generator and transmission line are 1.2 ohms and 0.8 ohms. The terminal voltage of synchronous generator is given as 15 kV. If generator delivers 70 megawatt power to infinite bus bar, then the load angle delta is. So this formula we know here. What is formula to find PE? It is EV by X sin delta. PE how much? 70 megawatts. E how much? 15 kV. EV how much? 11 kV. What is the total reactance? Generator 1.2, line 0.8. From this we calculate what is the value of delta. So delta value you get 58.04 degrees. So how much delta you get? 58.04 degrees. Now we solve this next question. A 2-pole 50 Hz (11 kV) turbo generator has a rating of 60 megawatts, power factor 0.85 lagging. Its rotor has a moment of inertia of 8,800 kg meters square. The inertia constant in megajoules per MVA and its momentum in megajoules second per electrical degree is. So first we have to calculate what is H. H, how you calculate? Kinetic energy stored. So half I omega square divided by rating is S. How much the moment of inertia is given in the question? 8,800. Omega, how you write? 2 pi n by 60. N is how much? 120 F by P. That is 3000 RPM. What is the MVA rating? 60 megawatts. MVA rating means divided with the power factor. You divide with the power factor. So multiply this total and verify. You get the answer 6.152. Here it is megajoules here, the megawatt. 6.152 megajoules per MVA. In the last section we defined inertia constant how much? Half I omega square by S. You know omega is 2 pi F. Omega is 2 pi n by 60. And what about n? You know it is 120 F by P. Now we have to find out the momentum. What is formula to find M? SH by pi F. Or you write GH by pi F. S and G are same place, the MVA rating. S, how you write? P by cos phi multiplied with H by pi F. So how much? 60 megawatts by 0.85. H how much? H value is given in the question 6.152. You want in degrees, so write 180 degrees. F frequency is 50. So you need not mention the megajoules here, megawatts here. You simplify as it is. And directly you get it in MVA. Same you represent here. So simplify this one and verify the answer here. So this is how you calculate what is inertia constant H. Half I omega square by S. S you write P by cos phi. Let it be in megawatts. By cos phi will become MVA. The denominator is in MVA. So on simplifying this one, think you get 0.04825. So many megajoules second per electrical degrees. So simplify. you get the answer in megajoule seconds per electrical degrees. So just based on the formula, you substitute the data given in the question. Accordingly, you get these answers here. Now we solve this next question. A 500 megawatt, 21 kV, 50 hertz, 3-phase, 2-pole, synchronous generator having rated power factor equal to 0.9 have the moment of inertia 27.5 into 10 cube kg meter square. Inertia constant is. So you know the formula for H. How you write? The energy stored by the rotor. How much? Half I omega square by S. So now you substitute the values there. Half into how much given? Moment of inertia 27.5 10 cube. Omega is 2 pi n by 60. N how much? 120. F by P you get 3000. Whole divided by S is P by cos phi. 500 by power factor is 0.9. So how much you get on simplifying this one? So you get 2.44 megajoules per MV. How much you get? 2.44 megajoules per MVA. Now we solve this next question. A 50 hertz, 4-pole turbo generator and 20 MVA, 13.2 kV has inertia constant 9 kilowatt second per kVA. Shaft input less rotational losses is shaft input less the rotational losses is 26,800 horsepower electrical power developed is 16,000 kilowatts. So we have to calculate the first part of the question. Kinetic energy stored in the rotor at the synchronous speed. Second part of the question is accelerating torque is. How you find the kinetic energy? S into H. S how much? 20 MVA. Now, watt second is what? Joules. 9 kilojoules per kVA can be written as 9 megajoules per MVA. So you get the answer 180 megajoules. Now how to find out accelerating torque? TA you write it as PA by omega. PA how you write? PS minus PE. How much PS? The mechanical input is 26,800. But it is in horsepower. So multiply with 0.736. Electrical output is 16,000. What about omega? Is 2 pi n. So 1500. So on simplifying this one, you get the answer 23.1 Newton meters. So on simplifying, you get the answer as 23.1 Newton meters. Now we solve this next question. A synchronous generator with a synchronous reactance of 1.3 per unit is connected to an infinite bus whose voltage is 1 per unit through an equivalent reactance of 0.2 per unit. For maximum output of 1.2 per unit, alternator EMF must be. It's what you have to calculate. So what is PE now? You write EV by X. PE how much? 1.2. E is what we have to calculate. B is 1, X is 1.5. So from this you find out E, you get it as 1.8 per unit. So on simplifying, you get the answer as 1.8 per unit. Now we solve this next question. This is asked in one of the civils question paper. A three-phase line having negligible resistance and 22 ohms inductive reactance per phase operates with 110 kV sending end voltage and 100 kV receiving end voltage. Maximum power that this line can transmit is. So what is the formula for PE maximum? Is the steady state stability limit. Formula is EV by X. E how much? 110 kV. V is 100 kV. This 22 ohms. So on simplifying this one, you get the answer as 500 megawatts. So you get the answer as how much? 500 megawatts. Now we solve this next question, dealing with finding the roots of characteristic equation here. A synchronous generator is having synchronous reactance of 1.25 per unit connected to a infinite bus through a transformer and transmission line. Infinite bus voltage is 1 per unit. And excitation voltage is 1.2 per unit. The reactance of transformer and transmission line is 0.6 per unit. inertia constant of synchronous generator is 4 megajoules per MVA. So now we have to calculate the frequency of rotor oscillations in hertz. If alternator delivers 50% of the maximum power initially is. So this is what you have to calculate here. So you verify the question here. First we are having an alternator, its reactance, then step-up transformer and a line connected to infinite bus bar. This total reactance given of transformer and transmission line, how much? 0.6. What about E? 1.2 angle delta. This reactance is 1.2 per unit. So it is 1.2, please. Reactance is 1.2. Now we have to find out the rotor oscillations. First to find out what is delta naught. How to find? We know initially PS same as PE naught. This question is based on our last topic, analysis of steady state stability using swing equation. So before increase in the load demand, how much PS is PE naught? We write it as EV by X equivalent sine delta naught. Or you write PM sine delta naught. EV by X equivalent is PM. But how much you are delivering there? PE naught? 50% of maximum power. So on simplifying this one, what is the value of delta naught? Is 30 degrees. Then you find what is dou PE by dou delta evaluated at delta naught. So you know this EV by X equivalent, now cos delta, where delta is delta naught. E is 1.2, V is 1, total reactance 1.8, cos 30 degrees. On simplifying you get 0.577. Next to calculate what is M. You know the formula SH by 1 pi F. Now what is H given? How much? 4. Now important step. What is the value of S now? Are you given any MVA rating in the question? Not given. Or megawatt rating power factor are also not given. So you take the alternator rating as the base value. So what will be the corresponding per unit value? Its value is 1. Corresponding per unit value is 1. So how much this F is now? 50. Now lastly you can find out what is the value of K. You have analyzed in the derivation what is K. You have written 1 by M minus dou PE by dou naught, dou delta, evaluated at delta naught, under root. This is in the radians per second. So we substitute the data and calculate. So 1 by 4 by 180 into 50 minus of dou PE by dou delta. How much it is? Minus 0.577. So on simplifying you get plus or minus j 0.48. So what is the frequency now? Sir, it is 4.8. You have the negative term inside. So the roots are complex conjugate. So this 4.8 is in radians per second. How to convert this to hertz? Divide with 2 pi, you get the answer in hertz. How much on dividing with 2 pi? You get 0.76 hertz. So when the rotor is delivering 50% of initial power initially, the frequency of rotor oscillations is 0.76 hertz. Now to obtain a conclusion here, to obtain the conclusion here, we solve this last question for today session. Say now, alternator is delivering 80% of power initially. So if it is 80%, all these values changes. So how much delta naught is? 53.13 degrees. What about dou PE by dou delta here? It is 0.4. How much that value is? 0.4. So how much you get? If you substitute 0.4 here, you get 3.96 radians per second. So now the frequency is 3.96 radians per second. How to convert this to hertz? Divide with 2 pi. How much you get? 0.63 hertz. 0.63 hertz. So what is it you conclude from these two questions? Earlier alternator is loaded only for 50% of maximum power, frequency 0.76 hertz. Now alternator is loaded to 80% of maximum power, frequency decreased to 0.63. So what we conclude is, as the loading on the alternator increases, the frequency of rotor oscillations decreases. So the conclusion is, as the loading on the alternator increases, the frequency of the rotor oscillations decreases. So these are, you analyze and determine what is the frequency of rotor oscillations corresponding to the last two questions here. Now we have few questions. First question is by Purushottam from Jaipur. Why with asynchronous machine PA equal to 0 condition is not achieved? Because you don't have any control regarding the shaft input, the steam input. With synchronous machine you can achieve that condition. Next question is by Vishwam from Agartala. how stator axis remains constant with respect to reference axis always, because for any change in the load, only the position of rotor with respect to stator changes, that is delta changes, but the position of stator with respect to reference axis gamma is not affected by the change in the load demand. So whatever may be the change in the load demand, the position of stator axis with respect to reference axis remains unchanged. Therefore, you consider stator axis as the reference axis. So with this we conclude today's session.